All right, so it's past 3:30 now here in Indiana. So I think we can go ahead and get started. See, there are thunderstorms in Bloomington. So there is the chance that some of us may get disconnected temporarily at some point during the storm. I am not personally in Bloomington. I'm in Indianapolis, where we had thunderstorms last night. So I've been experiencing power outages. So on that note, if I suddenly disappear, I'll be back as soon as I get power. Now we're going to pick back up with the COVID simulation, and we're going to use this as a vehicle to do some very simple parameter variations, but we're going to do them programmatically. So we're actually going to go back into Player and Tweet it. We're going to load some simulation files, and we're going to do some very simple modifications to the actual simulation scripts. Now we're going to start by doing another brief review of using Player and Tweet it. Just want to get this down now and early so that once we actually get to the model development and the actual coding, that everyone is comfortable with using those well enough to be able to make some of the magic happen. And then we'll get right to the variations and the coding. So unless there are any objections, let's get started. So we're going to start with addressing a question that came up in the last module, which was, can we run the simulations locally? So we had the NanoHub tool going, and that's nice. It's nice to have that available to run via the browser. But for some of us, the local installation is preferred, myself included. So everything that we do on this particular project is maintained on our GitHub page. So you can always find exactly where this project is currently by going to this page. I'm going to drop the link in the chat. So this is the link here for anyone who is working locally and would like to do these couple of exercises, as well as just have this model in general for your local installation. This link is in the chat to quickly grab that. Now, for those of you who are going the GitHub route, this will take you to the page shown here in the screenshot. And you can download the entire repository locally by clicking the green clone button. And then that will present this blue button, download zip. So that'll be a compressed version of the entire archive. And in that download, you can find all of the simulation files through this path. Now, for those of you who want to work locally but are GitHub allergic, files are also available by Google Drive. This version will be a couple of versions behind, but all functionality and model mechanisms are the same. I think this version is just a little slower than the current one. So to download the files without GitHub, this link is in the chat. You can follow that, and that'll take you to the same simulation files, just missing a couple of performance improvements. Now, for those of you running NanoHub, should already have the tool launched. for anyone who may have closed it and need the link again, the link is in the chat. Again, that's the NanoHub tool that's specific to this project. So you can follow that if you want to work in browser and not deal with the installation. And that should take you right back to where we were in module 1.3, which I have already pulled up and have loaded. I'm going to jump back and forth actually between my NanoHub tool and my local installation. There are some subtle differences that Juliana's already covered. We'll review those again very briefly. So I'm going to split my screen here. I'm going to start in NanoHub. And let's review very quickly loading a simulation into Player. So the NanoHub tool will launch and will automatically start a simulation. Again, you can stop it by hitting the stop button in Player. That's the fourth button in the top left. And you can go to, in the menu bar, go to File, and Open Simulation File. You select that. Again, everything is in, on NanoHub, everything is in your personal directory, which is shown here on the left. My username is TJ Sego, so all of my stuff is in this directory, TJ Sego. This was the same directory that was being navigated to in module 1.1. You'll notice in this particular tool, there are quite a few less options. So in your personal directory on the left, select that, and then CompuCell3D demos. You go into there by double clicking, and you can select coronavirus and go into there. And that takes you to viral infection VTM.CC3D. This is the same procedure as reviewed earlier with Giuliano. In this particular case, this is using the NanoHub tool. But the same is true for all other projects in the general CompuCell NanoHub tool. Now, in the local installation, again, the process is the same. Well, very similar. So in the menu bar, File, and then Open Simulation File, and navigate to wherever you downloaded your local version of the model. And you'll want to find the file viral infection VTM.CC3D. So select that and click Open. You'll see along the top, should say viral infection VTM.CC3D. And that means that it's loaded. Now, if everyone's here, we can proceed to Twedit. So Twedit can be quickly launched again from Player using this icon that I'm currently hovering over. Looks like a little page with a pen or a marker. You hover over it, it should say Start Twedit++. So you can just click that. That automatically launches Twedit. The same is true in the NanoHub tool. So NanoHub, the same button is there. It says Start Twedit. You click that. And that launches TweetIt. Going to resize my NanoHub tool very quickly. Okay. Now in TweetIt, loading simulations is the same basic procedure, except in this case in TweetIt, you go in the menu bar to CC3D project, and then open CC3D project. Again in NanoHub, it doesn't take you automatically to viral infection vtm.cc3d. Again, on NanoHub, you can access your personal directory by clicking the folder that has the same name as your username on the left. You can find it under CompuCell 3D demos, and then coronavirus, viral infection vtm.cc3d. Do the same locally. Once in TweetIt, in the menu bar, CC3D project, open CC3D project, and then find viral infection vtm.cc3d in the files that you downloaded. Select that and click open. Now on the left pane that's named CC3D simulation, you should find a selectable entry. It says viral infection vtm.cc3d. Let's double click that. So simulation pane, double click viral infection vtm.cc3d. Now what you should find is a lot of simulation files, many more than the demos that were reviewed earlier today, and much of that is to do with that it's a big model, and we won't be building anything nearly this complex this week. We certainly won't be going really into any of these files now, but for bigger models, it's certainly possible to start dividing up model structure into individual scripts to do more advanced programming strategies and techniques to sort of manage big models like what we reviewed in the previous module. And you can see a list here on the left of how this particular simulation is divided up. So there's some XML specification in one script, and then with all the Python scripts, some of them define the actual model specification of doing things like viral internalization and so on and so forth. There are other scripts that more are just sort of a dump for utility functions that aren't particularly pretty and fun to play with. And then most importantly for what we'll do today is a script called viral infection vtm model inputs.py. And this is the model script that contains all of the input parameters for the entire model. And when you double click viral infection vtm model inputs.py, it should automatically open the script in your text editor window. You can scroll down just quite a lot that's specified here. Almost 300 lines just of declaring and annotating parameters. So this is where we'll be working today for this module. We're going to do a couple of simple parameter variations in here instead of using the sliders. Now in the script viral infection vtm steppables.py, we're not going to really get into this very much, but just as sort of a vision of what this sort of looks like as far as CC3D based model development, you'll notice in this list here I've made in this slide, there are lots of individual entries with the suffix steppable, cell initializer steppable, viral internalization steppable. Each of these are specified in viral infection VTM steppables.py, and each of these is a separate Python class where model specification is performed. So this tells CompuCell how to simulate whatever you'd like to model. But each of these is divided up by a particular mechanism. And so when doing modeling of lots of biological complexity, this structure that CC3D is built to do, this is a really great way of being able to partition the complexity of a particular modeling problem and divide it up into individual mechanisms. So for a big model like this, this is what it tends to look like. It's something like this. Again, we're not going to get into this today, but in our model building modules, we will end up designing steppables. So in viral infection VTM model inputs, there's almost 300 lines of code just for model parameters. And here's a summary of all of them with the baseline parameters, no particular value of which is important at the moment, but more so just to get a sense of really how much information is actually going into this, how many different parameters can actually be individually varied to study differences in emergent behavior of the complex dynamics of viral infection and simulation. So we are going to do the same parameter variation that we did in the previous module, but instead of using the sliders, instead we're going to do this programmatically. It's a question in the chat for CC3D files. Does it contain all of these Python scripts, or is it more likely an index and all these codes have to be arranged in defined structures? So all of this is imported into CompuCell as something like a Python module, and the information that's specified to tell CompuCell what all is there is very simply done in one particular script, which is the CC3D file. But really the CC3D file is more so arranging this information and categorizing what files are what, which can all be done manually. But otherwise, this imports into CompuCell like any other class or set of classes. So in this file, viral infection VTM.py, this is one of the types of scripts that are automatically generated when generating one of these projects using our wizard. And for those of you who are familiar with Python, this might look familiar. This is just a simple script that will import each of those steppables from our steppable script and then tell CompuCell to run it. And it's as simple as that. Excuse me. See a question, issue in the chat. Files won't open in CC3D on NanoHub. The error says that the files aren't accessible. I can, however, see the list of files after I load the simulation in CC3D. Is that an issue in Player or Twedit? Because I'm curious about why I don't see that issue on mine in Twedit. Same problem with desktop version in Twedit, that the files won't open. That's interesting. Not a problem I've seen. Well, let's yeah, just walk through the process again very quickly. So in Twedit, CC3D project, then open CC3D project. If you're on NanoHub, want to select the directory. If your username on the left, and then CompuCell 3D demos, coronavirus, viral infection btm.cc3d. So the CC3D file is what you want to actually select and open. So select viral infection btm.cc3d and then select open. And it's the same locally. It's CC3D project, and then open CC3D project in the menu bar. And then you navigate to where you downloaded the model and specifically find the CC3D file, viral infection btm.cc3d, and select the file and then select open. Okay, so now let's do our parameter variation, but let's do it in Twedit. So when we modified the parameter k_on in module 1.3, we had our steering parameter and we selected an item for k_on multiplier. And we increased that by a factor of 100. What that was actually doing was modifying this parameter, k_on. This is the expression for the probability of infection. And in particular, when increasing k_on, this will lead to a corresponding increase in the probability of internalization for a given amount of virus. Now, we multiplied that by 100 in module 1.3. Let's do that again. Let's do that in Twedit this time. So you can navigate down in viral infection btm model inputs.py, and you can just select that in Twedit and double click it. I'm going to go down to around line 264. And you should see k_on. This big long expression with lots of conversion factor calculations. Now to do that same parameter variation that we did beforehand in module 1.3, we can do that same thing by just multiplying this expression by 100. Now you'll notice that it's already multiplied by 100. That is part of the baseline parameter set. So to do the same multiplication by a factor of 100, just go to the end of line 264, approximately, for where k_on is declared, and just multiply it by 100. So you should actually have 2 instances of times 100. Now again, you'll notice in Twedit in the top along the tabs for the various files of this project that the disk for viral infection btm model inputs.py is turned red. That's due to unsaved changes. Those unsaved changes will not be reflected in player when running this. Player will only reflect changes that have been saved. So you can save that using your hotkeys. In Windows, it's Control S. I don't know the hotkeys on other operating systems off the top of my head, but you also have the button in the top left with this big black down arrow. It saves CC3D project. You should see that all of the disks are blue again. So now the changes that we've made will be reflected in player. So if everyone has multiplied K on by 100, I see in the chat, I see Max Secrete IM. I believe you would be at line 166. So the line numbers on some versions of Twedit are a little hard to see. If you have a mouse wheel, you can deal with that by zooming out a little bit in the text editor. So if you hover your mouse over the text editor and have a mouse wheel, you can hold Control and then roll your mouse wheel. You can zoom in and out. If you zoom out a little bit, you can see the line numbers a little better. That's been fixed in a new version of CompuCell. So if you're at Max Secrete IM, you're at line 166 approximately. Go down a little bit farther. You can also search doing Control F on Windows and just search for K on. K on, and then find next. And that'll take you down to here. Question, the inputs, yeah, viral infection VTM model inputs is the input script. And then line 264, multiply by 100. Now, let's go back to player. So if everything is saved, we've already loaded viral infection VTM.cc3D. Then when we hit play, we ought to see fast infection again. So let's do that. Everything's saved in Twedit. We've done our times 100 multiplier. Let's hit run in player. It's the first button in the top left. You can organize your window again by in the menu bar going to window and then tile. I'm going to maximize my screen, minimize the steering panel. Yours is running much slower than mine on NanoHub. It's just a difference in hardware, nothing to be concerned about otherwise. See lots of infection in my cell field. Again, if you don't have a cell field window at the moment showing either epithelial cells or the immune cells, you can hit the new graphics window button or go in the menu bar to window and new graphics window. My CompuCell just crashed, so I'll switch to NanoHub. So it should see infection taking off very quickly. James pointed out a good point in the chat that when changing parameters in Twedit, so making programmatic changes to the actual simulation scripts, those changes are not reflected in a simulation that is running. The steering panel is a tool that we use to be able to make changes to parameters mid-simulation. But to make changes in the code reflected in player, the code itself has to be reloaded, meaning that the simulation in player needs to be stopped and restarted to reflect a change in the code. Let that run for a minute. What we would expect to see is within the first couple hundred simulation steps, yeah, mine's already taken off. In the first couple hundred simulation steps, just as we observed earlier in module 1.3, should see infection take off quite fast. And by fast, I mean fast with respect to our baseline parameter set, where at around 500 simulation steps, infection was about half of, maybe a little more than half of the simulation domain. Now, I'd also like to point out that using the NanoHub tool, the steering panel is still available. And the changes that we made in the code, you don't see that here. Steering panel still initializes with multiplier values, all equal to 1. So the changes that we made in the code then are added to whatever multipliers we assign in the steering panel, meaning that our new initial value for K on is 100 times what it was, in which case if we then apply in the steering panel a multiplier of 100, then we've increased K on from the baseline parameter set by a factor of 100 squared. I definitely see the same characteristics as in module 1.3 when we did the steering panel parameter variation, coming up on 175 simulation steps and certainly faster spread of infection. It's a much bigger region of virus releasing cells than the baseline parameter set, already starting to get some sparsely distributed infection sites So aside from the stochasticity from the higher level qualitative behaviors of it, this is doing approximately the same thing as the parameter variation we did in module 1.3. So we can stop this simulation. In the top left, you hit the 4th button, or you can leave it running while we talk through the next variation. We're going to do one more and then compiled a list of some other interesting ones to do as well. Would like to do a second one, which is varying the replication rate. So this again is the exponential amplification of the virus in the model. This is where the viral load exponential growth comes from. And the coefficient that's made available in the steering panel that we're going to modify programmatically is this coefficient Rmax, which in CompuCell is written as the replicating rate. And you'll notice that this just multiplies this replication term, in which case when we increase Rmax, genomic replication increases. And when we reduce it, the rate of genomic replication will decrease. So let's start by going back to Twedit. I'm going to give my local CompuCell another try. Okay, so let's begin by reversing the parameter variation that we just did in the previous exercise. So let's go to line 264, or you can just search for K on Windows. You can just press Control F and search for K on, and click Find Next. Around line 264, let's go to the end and remove the times 100 multiplier that we added in the previous exercise. So when you remove the modification that we made, then your K on expression should only have one instance of times 100. Again, that is a part of the baseline parameter calculations. It's times 100. So it should only be one instance of times 100. Now, let's change the replicating rate. So if we go up from K on to around line 145, should find an expression that looks like my screen as well as in the slide. Replicating rate equals some stuff. Now, I want to see more fast infection, because fast infection is more interesting to watch than no infection. So let's do a variation of the replicating rate. Let's multiply it by 2. This is the baseline parameter set. Just go to the end of line 145 and add times 2. So we insert times 2 at the end of line 145. Question in the chat about built-in tools for parameter scans. There are. Yeah, there's built-in functionality for parameter scans that I believe is scheduled to be surveyed on day 4 of the workshop. And that's for built-in features using JSON files and some other techniques. There are also ways to do this purely in Python that are newer features to CompuCell that we're still kind of working on developing. So the parameter scan or sweeps that were shown in the previous module, those were all implemented in Python by some things that I built. And then we have some built-in features that are currently included in the distribution. Okay, so line 145, multiplied it by 2. Make sure and hit save. Should have green disks along the top, the tabs for the file names. Got green disks and a ×2 multiplier. Let's go back to player. Forgive me if mine crashes again. I'll just switch to NanoHub. I'm going to try it. If you got a simulation running, hit stop, 4th button on the top left, and then hit run. Now, one thing to notice, I believe this pops up in the NanoHub tool as well. Yeah. So in the NanoHub tool and in the local installation, one of the data windows, let's see, does this show up in NanoHub? It does not. That's fine. Okay. So now I'm running mine and I'm coming up on 100 steps. And my infection in my simulation is taking off even faster than the last parameter variation. I have a very noticeable central core of virus-releasing cells that seems to be expanding almost faster than the ring of infected cells. My simulation isn't even at 200 steps, and this infection area is comparable already to where the baseline parameter set was at 500 simulation steps. And that was for, again, a multiplication factor of 2 on the replicating rate. And this is the effect of amplifying exponential amplification by a factor of 2. You see a corresponding huge change in the behavior of the system. Still got the same sort of outcome of widespread infection, where there's a central core of dead cells, got a ring of virus-releasing cells, it's much thicker in this case, and then infected cells on the outside. In this case, my simulation replica had complete infection by around 320 simulation steps. And then compare that to the baseline parameter set, where this outcome, when it occurs closer to 800 to 900, sometimes closer to 1,000 simulation steps. It is a huge effect just by simply doubling one model parameter. Now you can let that run if you'd like to watch the tissue damage progress. At this point, this tissue is pretty much a goner, but you can see instances of contact killing for the remaining virus releasing cells. You can also notice if you're looking at, say, the data plotting for the immune response, it's an example of a high pro-inflammatory state and then lots of corresponding immune cells. If you watch that play out for long enough, you'll see the pro-inflammatory state subside because there's no more signaling, because there are no more cells to signal, and that'll go towards zero and the immune cells will start disappearing. Now, you can go back to TWEDIT and change the replicating rate back to what it was originally. So you can just go back to line 145 and viral infection VTM model inputs.py. Line 145, just remove the ×2 multiplier. And the state of this simulation is back to the baseline parameter set, in which case you have an exact copy of the simulations used for the results that we reviewed in module 1.3, and that's gone into the paper as well. It's the exact copy that we are currently building on through various projects and modeling. Lots of the mechanisms that were discussed that haven't been included here, things like phagocytosis and interferon signaling for viral resistance, so on and so forth. Now, I have quite a few more exercises actually developed to do in this module, but we have been progressively getting later and later on our schedule for today. So instead, we have uploaded a complete schedule of all of these exercises. So each of these variations is uploaded to the shared files for the workshop. There are six different variations, one of which is a combination of parameters to vary. And that schedule will describe where the different lines are. You can see it in the screenshots as well. And the schedule also outlines what parameters to vary to do something interesting. So you can go to the shared workshop files to find the schedule for all of these 6 exercises. And maybe after the day today, you can do some of those on your own time using your local installation or the NanoHub tool. And then, of course, can reach out to any of us for anything that might have interested you, something interesting that you might have found, as well as, of course, ideas on how to improve the thing. So with that in mind, I'd like to turn this over to Q&A, and then we'll move on to 1.5 and start getting into some actual preliminaries for model building for the workshop. There's a question, why is there a large variation in energy between flips? This would be the energy calculations shown here in the console on mine and the local installations and the NanoHub tool as well. Yeah, these reports of energy calculations. So this is a reporting of the calculations of the cellular POTS model. That's the cellular dynamics engine behind CompuCell. And as James mentioned, and we discussed in the previous module, there is lots of stochasticity in these models, and there's in fact stochasticity involved in the actual cellular dynamics itself. So these energy calculations showing increases and decreases, this actually has to do with the governing probability of the different events of surface fluctuations of the cells. Most notably, that energy increases actually dictate a probability of displacement of surfaces, where the probability decreases with increasing energy. So when you see positive energy changes, you know that there were a lot like stochastic events that certainly contributed to this positive value. And this is an overall reporting of an effective Hamiltonian that is used to do all of our model mechanisms in the cellular POTS model. So when you see it go up and down like that, those fluctuations, that has lots to do with all of the underlying stochastic dynamics behind the cellular dynamics itself. Okay, unless there are any more questions. There's a question about showing the data plots in this particular set of simulation scripts. So if you go back to TWEDIT, I'm just going to go full screen on TWEDIT for a second. If you go back to TWEDIT and go to viral infection VTM model inputs.py, you go all the way up to the top. You'll notice that there are these different variables in this first block. They're combinations of the prefixes plot and write. So plot VRM data, write VRM data. Plot pop data, write pop data. So these are options to specify the frequency at which to update various data reporting windows. Population data and immune response model, those are distributed as currently being active and reporting at 10, one reporting every 10 steps. But there are lots of other ones that you can also enable. Disabled ones are set to 0. You can enable them by changing those frequency values to non-zero. And you can also write that data by setting the corresponding write variable. So this was distributed with plotting the population data at a frequency of 10. You could also write that at a frequency of, say, 1 by going down to line 24 and doing write pop data frequency. And there are lots of other ones that weren't distributed as being automatically enabled, but you can definitely enable those and take a look at some of the other interesting data during simulation. Okay, unless there are any more questions, we'll maybe take a 2 or 3 minute break, I think. James, we'll let you drive from here.